Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
In this problem, we are given the length of a wire, and we know that it's made into a coil of one turn, and we know the current going through that wire and the magnetic field with which the wire is suspended. And then we're asked to find what the maximum torque is on that one turn circular coil. Well, if we look at the equation for the torque on a coil in a magnetic field, it's given by the number of turns times the current through that coil times the cross-sectional area of that coil times the magnitude of the magnetic field in which the coil is suspended, multiplied by sine of phi, where phi is the angle between the normal of our coil, so the normal sticking out of the cross-sectional area of our coil, between that vector and the vector direction of our magnetic field. Now, when the torque is a maximum, or I should say, the torque will be a maximum when phi is 90 degrees, or sine of phi, so sine of 90 degrees is 1, right? Remember, sine function varies from 0 to 1, and therefore, if we want the maximum amount of torque, we want to solve this equation for when sine of phi is 1, or sine of 90 degrees is 1, or sine of phi is 1, and that just goes away. So we have an expression for the maximum amount of torque that is just NIAB. Now, we're given much of the information we need. We know that it is only a one-turn coil. We know the current going through that coil, but we don't know the cross-sectional area. We only know the length of the wire of this coil. So we know, though, we have some wire of length, we'll call it little l, and that this wire is made into a circle. Right, so if this wire is made into a circle from a wire of length l, we know that the circumference of that circle must equal the length of that wire. So from this, we can try to figure out what the area will be, not in terms of the radius of the circle, but in terms of the circumference of the circle. So let's just do a little bit of exploration algebraically to figure that out. So how do we do this, right? Well, we want an expression for the area, cross-sectional area of this circle, and that, of course, is just going to be pi r squared. So if we knew the radius of this circle, we could figure out the cross-sectional area. Of course, we don't quite know the radius, but we do know a relationship between the circumference, which we know is L, and the circumference of a circle, which is 2 pi times r. So we can use this equation to solve for r in terms of the length of our wire, which is the length divided by 2 pi, and then we can plug that in to the equation for our area. So if we do that right here, the area is going to be pi r all squared, but r is L over 2 pi. When we square all this, we're left with a pi times L squared divided by 4 pi squared. So the area can be expressed in terms of the length of this wire, and it's given by the length squared divided by 4 pi. So that is the area now in terms of something that we know. And let me draw my pi a little bit better here. Well, I'll just rewrite the whole thing. 4 pi. And so that's going to be a relationship between the cross-sectional area and the length of the wire. And the length of the wire is something we know. Cool. So now I have an expression for the maximum torque, which is what we're trying to find here. And now I know how to express my area in terms of the length. So I'm going to replace A with L squared over 4 pi. And then, of course, I have my magnetic field term here. So I plug all the numbers in that I know because I do know the current. It's 4.3 amps. Remember, I plugged in 1 for my number of turns already. Multiply by 7.00 times 10 to the negative 2 meters all squared. That's the length of our wire. Divide that by 4 pi, and then multiply by our 2.50 Tesla magnetic field. So I plug all this in my calculator. What do I get in the end? I get an answer of about 4.19 times 10 to the negative 3 Newton meters. That is the magnitude of the torque that this coil is feeling, the maximum torque that this coil experiences in this magnetic field.